Today we'll start how do you measure the low resistance, measurement of low resistance using Kelvin's double bridge. You can look at here. So before getting to that Kelvin's double bridge students, let us start which topic I have completed in earlier, that is Wheatstone bridge, and I didn't discuss about limitations. So let me discuss about limitations first. Limitations of Wheatstone bridge. The effect of lead resistance and contact resistance is very much significant while measuring low resistances. So the bridge cannot be used for high resistance measurement, that is measurement in high mega ohm range. This is because while such measurement, the resistance prevented by the bridge becomes so large that the galvanometer becomes insensitive to show any imbalance. Similarly, heating effect due to large current also plays a major role. The excessive currents may generate heat, which may cause the permanent change in the resistance. So, the resistance used must be very precise, having tolerance up to 1% or 0.1%, hence cost is high. So now we'll come to the measurement of low resistance, that is using Kelvin's double bridge or Kelvin's bridge. In the Wheatstone bridge, the bridge contact and lead resistance causes significant error while measuring low resistances. Thus, for measuring the values of resistance below 1 ohm, the modified form of Wheatstone bridge is used, that is known as Kelvin's bridge. The consideration of the effect of contact and less lead resistance is the basic aim of the Kelvin's bridge. So you can see here, looking at the Kelvin's bridge, here in the diagram, the resistance, what you are seeing here, represents the resistance of the connecting leads from R3 to Rx. That is here. R and S. You can look at this R and S. Okay, the galvanometer can be connected to either terminal. Here it's not shown, students, but you can name it as ABCD, AB or terminal C. So when it is connected to A, the lead resistance or Y gets added to Rx. Okay, so here the lead resistance, this one is added to this. This will be added to this S. Hence, the value measured by the bridge indicates much higher value for this S. If the galvanometer is connected to terminal C, in case if it is to which terminal it is connected, so either to M or it is connected to N. So here M or N, whether you are connecting to M or N or C. At the center you have C. Okay. So now, if the galvanometer is connected to terminal N, what happens then? Ry gets added to what? R. Then it's get added to R. This results in the measurement of S much lower than the actual value. So the point C is in the points between the points M and N in such a way that the ratio of the resistance from M to N to M and that from, please listen to me, here M to C is equal to the ratio of what? Is equal to the ratio of Q by P. Okay, that's why it is R1 by R2 is equal to P by Q. And you can look at the relation R1 by is equal to R1 plus R2, which is equal to P by P plus Q. How it is written? Now the bridge balance equation in its standard form can be written. How do you write it? This you can see using the standard relation, that is R is equal to PS by that relation. You can say Q by R is equal to P by S. So using that relation, here students, Q into R is equal to P into S. That is a standard bridge balance equation in its standard form. So now using that relation, you can see here the steps you can understand. Each and every step is self-explanatory, simple mathematical steps. So you are landing up with a just you have to multiply and divide. That's all we are doing here. And finally, we land up with the equation R is equal to PS by Q. This equation represents the standard bridge balance equation for the Wheatstone bridge. Thus, the effect of the connecting lead resistance is completely eliminated by connecting the galvanometer to an intermediate position, that is to an intermediate position C. This principle forms the basis of the construction of Kelvin's double bridge, which is popularly called Kelvin bridge. Now, let us go how to find the measurement of earth resistance. So you know that measurement of earth resistance here in the topic there are two methods which are used basically for the measurement of earth resistance. That is, one is fall off potential method, other one is using Mecker earth tester. So now let us discuss about fall off potential method. You can see here the figure you are seeing, that is circuit diagram. It is used for the measurement of earth resistance by fall off potential method. So here E is the earth potential, E is the earth electrode, E is the earth electrode, and the electrode Q is the auxiliary electrode. The current I is passed through the electrodes E and Q with the help of external battery. So here another auxiliary electrode will be introduced, and then here when it is introduced between the two electrodes E and Q, the voltage between the electrodes E and P is measured with the help of voltmeter. Let this voltage be V for the known current I. Now, the pattern of the current flow in the earth from electrode P to Q is actually there. The pattern will be developed. The current diverges from the electrode E while converge at the electrode Q. So, near the electrode E, the current density will be very, very high. Similarly, near electrode Q also current density is high. Thus, if the distance of electrode P is changed from electrode E and electrode Q, the electrode P experiences a change in potential near the electrodes, while a constant potential between the electrodes but away from the electrodes. Okay, such a potential variation between the electrodes E and Q is developed, and the potential rises near the electrodes E and Q due to higher current density. That because that is in the proximity of the electrodes. So while in the middle section, the potential will be constant. That's how the development of the electrode this will be distributed. So by measuring the potential between the electrodes E and P as VEP, the earth resistance can also be obtained. That is, RE is equal to VEP by I. That is actually the earth resistance. The measurement of VEP is done at many points by changing the position of the electrode P. So you can plot the graph against RE versus E, the distance between EP. Okay, so the true reading of RE is when the measurement is taken. When you plot it, you get the middle section AB will be flat. That when potential variation curve is absolutely flat, that the distance between P and Q must be sufficiently large to obtain the correct readings. So you can avoid the errors. So that completes the class 3.